We're not going to get super deep into this topic, but I do want to highlight a few things about these transformations of the other trigonometric functions. Specifically for the tangent and cotangent functions, there aren't a huge number of features for us to keep track of. Really, the things that we pay attention to most are going to be where the vertical asymptotes move. And then for the secant and cosecant functions, there just aren't that many applications that use those functions, and so it's not worth spending a huge amount of time on them. But it is worth exploring the general concepts to see how the same ideas can be applied to this one. So what do we have? So if we have a tangent or cotangent function, let's say we have y equals a times tangent of b t minus c plus d. All of these various parameters, a, b, c, and d, still impact the function the same way. The language is just slightly different. So for example, this right here still creates a vertical shift. The a value, instead of changing the amplitude, because with the tangent cotangent function there is no amplitude, it's just a stretching factor. And it's still in the vertical direction. The value of b, this also impacts, just as it did before, the period. Now specifically, because the tangent and cotangent functions have a period of pi, the new period is going to be pi over b. For the sine and cosine functions, this was 2 pi over b because the base functions had a period of 2 pi. In this case, because it's pi, it's just pi over b. This right here is still a horizontal shift term. Now, there is a little bit of nuance here with the horizontal shift because we talked about last time it sort of shifted to where the quote-unquote start of the function is. For this, in this case, we're actually just focusing on where 0 is. This actually shifts the location of that 0, and then we build out the function from there. So for the tangent, that's kind of in the middle of the shape. So for the tangent function, that point right there is your anchor point. And then for the cotangent function, it's actually that vertical asymptote at 0. That is your anchor point. But that's the point that you move in this horizontal shift term. So like I said, we're not going to spend a lot of time on this because it's not central to what we're doing, but it is useful to see the comparison and the ideas in this new context. We're going to do 2 examples. Graph y equals -2 tangent pi times t minus 1 plus 1, and y equals -2 cotangent pi times t minus 1 plus 1. And you'll notice that these two have a very similar form. The only thing that's different is the tangent turning into a cotangent. Over here we have the graph of the base functions. Notice that they both have period pi. The tangent function goes through the origin and has its vertical asymptotes at -pi/2 to pi/2. It's also an increasing function. The cotangent function is decreasing on the interval from 0 to pi and passes through 0 at pi/2. Okay, so let's think about this. How are we going to graph these functions? Well, we have to think about the same features. We have a midline. The midline is at y equals 1. We also have to think about the horizontal shift. Now remember, this horizontal shift is to the anchor point at the x equals 0, so in this case the origin, or in this case that vertical asymptote there. The horizontal shift is going to be 1 to the right. We have to think about the period. Now remember, the b value is not the period. The b value is related to the period. The period is going to be pi over b. And this is a pi over b instead of 2 pi over b because the period of tangent and cotangent is pi. Pi over pi is just 1. And then we have the vertical stretch and flip component. It's negative, so it is going to be flipped. And then the stretch factor, well, it's harder to plot these with a decent stretch factor unless you also include some additional points. We're really not going to worry about that. So it's going to be stretch vertically by 2 and flip. Okay, so now we have all this information. Let's go ahead and graph the first one. So the first one is the tangent function. Here are coordinate axes. Okay, so let's go through this. Midline, y equals 1. So we'll plot y equals 1. We also have the horizontal shift 1 to the right. So that tells us where this anchor point at the origin goes. So it's going to go 1 to the right. And it's going to cross through the y equals 1. That midline has been shifted up. And then to the left and right, we're going to have a half period in each direction. So period is 1, so a half period is 0.5. Like that. Now stretch vertically by 2 and then flipped. So again, if we really wanted to, at pi over 4, the tangent function is equal to 1. Tangent of pi over 4 is equal to 1. And so you could actually plot those points and make this a more precise graph. But again, for this class, for me, it's not so important to do that. The important thing here is, however, the flipping, because that affects how the shape is. So we're going to go down like that. That is a vertical asymptote. And then, of course, once we have this one period, we know that's going to keep repeating. The period is 1, so we'll go one more this way, so that's negative 0.5, and one this way is going to be 2.5. It's going to cross through the midline, and it's going to be decreasing because it's been flipped vertically. All right, so here's the graph of the tangent function. What about the cotangent function? The logic is going to be the same, and the only thing that changes really is the overall shape. So let's go through this again. Midline, y equals 1. What else do we have? We have a horizontal shift 1 to the right, and that corresponds to the x equals 0, which is going to be a vertical asymptote. So we have a vertical asymptote at x equals 1. The period is 1, so the next vertical asymptote will be at 2. And we know that it's going to go through the midline in between those two asymptotes. And in this case, when you flip this vertically, it's going to be an increasing function, so it's going to go up like that. And then, of course, we can use our periodicity to get the repeats of this function. Right. So the ideas here are very similar to what we've seen before. The shapes are different, and there are a couple of minor differences, such as the period changing. But basically, the same ideas hold as we did when we're looking at the sine and cosine functions. When graphing transformations of the secant and cosecant functions, there's actually a little trick that we can use. It actually goes back to thinking about the graphs of the underlying sine and cosine functions. So you might remember that we had graphed, in this case this is a sine function. If you're graphing the cosecant function, the zeros of the sine function created these vertical asymptotes. And then we took the min and max points and the vertical asymptotes and did this type of shape. It turns out that this same approach will work for any of the transformed secant or cosecant functions. So let's say you had the graph of a cosecant of b times t minus c plus d. If you wanted to graph this, you would actually first sketch out the graph of a sine b t minus c plus d, and then grab your min and max functions, the min and max values of this function, and then graph these sort of U-shaped things above and below, and make sure you graph your vertical asymptotes through the midlines, through where this crosses the midline of your sine function. So here's an example. Graph 3 secant of 2t minus 1. Now, part of the exercise of doing this is to remind you how to graph the cosine function, because the secant part is actually just going to be this thing we do at the end. And so let's look at 3 cosine of 2t minus 1. And let's think about the various bits and pieces that we need. Well, we're going to have to eventually get our key values all put together, but let's focus on this part first. Where is our midline going to be? That's easy to graph. It's going to be at negative 1. Right. Now, there is no horizontal shift because there's no c term there. The b value is 2, which means that the period is going to be 2 pi over 2, which is pi, which also means that our quarter period is going to be pi over 4. So we're going to use pi over 4 increments to mark off this x-axis, or I guess t-axis. Right. This 3 right here tells us that we're going to have an amplitude of 3, and since it's positive, it's not going to be flipped over. The cosine starts at the top, so that's where we're going to start. If the midline is negative 1 and the amplitude is 3, this is going to be height 2, and then the bottom of this, negative 1 minus 3, is going to be negative 4. And so it's going to be top midline, bottom, midline, top. And that's the pattern that's going to repeat. And we could actually get the coordinates of this. This is the point 0, 2. This is pi over 4, negative 1. This is 2 pi over 4, negative 4, and so on. So now what we need to do is we need to turn this into a graph of the secant function. How are we going to do that? Well, the way that it works is that we're first going to graph our asymptotes, and the asymptotes happen through the points where we cross our midline. Then we're going to take our max and our min values, and then just create the shape of the graph going this way. So there'll be another asymptote over here, and in fact that asymptote will happen at negative pi over 4, and you could do the same thing right here, and so on. And so you can see, really it just comes down to graphing the sine or cosine function, and then you just do this little thing at the end to turn this into a secant graph.